numbers on a paper.
Hello dear friends, welcome to Humble Mark Academy. In this video guys, we shall be looking at the circuit problem we have on screen guys. It's an LRO circuit, that is an inductor resistor circuit, right? Great. So guys, before I get started, I want us to introduce ourselves. I am Omenjo Macarius. In Humble Mark Academy guys, I take complex science problems, the ones that are very difficult for students to understand. I break it down into tiny pieces such that any student across the globe can use these concepts now to understand and score a better mark in his or her exams. In exchange guys, all you need to do is to press that subscribe button looking at you, because I can only help you to pass your exams once you subscribe to my channel. And friends, turn on your bell icon to get notified so that each time I upload the video, you're going to be the first person to get notified. Great. And friends, please give the video a thumbs up. That goes a long way to motivate me to keep creating more great content for you guys. Thank you very much, and please place your worries in the comment section down below so that I can know what the impression you have about the video. Great. So guys, let's get started. The question reads that E has a value of 100 volts, R1 has a value of 10.0 ohms, R2 20.0 ohms, R3 30.0 ohms, and L has a value of 2.00 henries. Great. Okay, now guys, immediately after the switch S is closed, what are A, I1 and I2? Then now they've given us something in bracket that let currents in the indicated direction have positive values and currents in the opposite directions have negative values. A long time after, what are I1 and I2? Then now they said the switch is then reopened. Just then, what are I1 and I2? A long time later, what are I1 and I2? All right. So guys, I'm going to be explaining every concept you need to know. And guys, even the physics involved, I am going to tell you guys everything. Now guys, we notice that this is a circuit that has both a resistor and an inductor, right? As such guys, it is going to behave slightly different from the normal resistor circuit that we all know. Okay, great. So guys, I'm going to show you guys a graph of how the current in the branch that has the inductor is going to vary with time. Okay, so guys, with the graph, we are going to have the current axis. Then guys, we have the time axis, that's the time in seconds. We have the current in amperes. Great. So this is going to be the origin guys. So friends, the graph is going to look something like this. Great. Initially, the current in the branch that has the inductor is going to be 0. That is at t equal to 0. We are going to have the current to be 0. Then after some time now, the current is going to grow in this manner exponentially. Then it's going to reach some certain value. Great. So we can indicate here that this is going to be that maximum value that the current through the branch that has the inductor is going to attain. We can give you some value I. Great. All right. Now friends, this all what we shall be doing in this video today, all the solution to this problem we have guys, everything has been summarized just with this graph. If you can understand the shape of this graph and properties about the graph, friends, means you're going to understand everything I shall be doing now. All right. So guys, the first part is saying that immediately after the switch S is closed, what are we have A, I1 and I2. All right. So now guys, we notice that immediately after the switch S is closed guys, we know for sure that there is no current that flows in the branch that has the inductor. Keep in mind that in the branch that has to do with the inductor guys, the current starts from a 0 value until it goes to some maximum value. But in the branch that has no inductor guys, as soon as the switch is closed, the current in the branch that has the inductor that has just the resistor guys attains a maximum value within the shortest time possible. So in this branch that has the inductor, initially just before the switch is closed, the current in this branch is 0. Great. So guys, in such a case, we can simply tell them that the current is equal to what? 0. Okay, the current across the branch that has the inductor is 0, and as such we see that R1 and R2 are in series, right? Great. since no current flows in this branch, since there's no current that flows, namely guys I3 is 0, it therefore means that this branch that's the inductor is not included in our circuit. That therefore implies our R1 and R2 are the only resistors under consideration, means they are both in series. And now guys, to get their combined resistance is simply going to be the sum of the individual resistances. Since resistors in series, their combined resistance, we simply get them by summing up their resistances. Great. That therefore implies guys R1 is what? R1 is 10.0 ohms, R2 is 20.0 ohms. So we do that, we have a value of 30.0, or we have 30 ohms. Great. Keep in mind friends that when the switch is closed, like I said, no current flows through the branch that has the inductor. No current flows there initially. Just when the switch is closed, no current flows there. It therefore means that the current in this case now has just one path. That is, it flows just from through R1 to R2, just in loop 1. Okay, this is how the current flows. And as such guys, R1 and R2 are in series, and we know for sure that in series current is the same, right? So we can tell them that I1 in this case has to be the same as I2. Great. And from Ohm's law we know that the current is simply going to be gotten as what guys? By taking the potential difference or the EMF of the cell, we divide it by what guys? The combined resistance of these two networks. So in this case we are therefore going to have our I1 now to be the same, like the potential difference or the EMF is simply what guys? 100. Then the combined resistance is what? 30 ohms. So we are going to have 100 over 30. When we do that, so we have a value of 3.33 amperes. Great. So guys, I1 is 3.33 amperes. I2 is as well 3.33 amperes by this our statement. Great. Alright, so guys, if there's something you didn't understand, feel free to leave it in the comment section down below guys. I'm going to get back to you as soon as possible. Alright, then now friends, they said let the currents in the indicated directions have positive values and those in the opposite directions have negative values. Great. They are now saying that after a long time, what are the currents I1 and I2? Great. Okay friends, what we should know is that for this inductor, like I said initially, when the switch is just closed initially, the current that is going to be flowing in the branch that has the inductor is going to be 0. But after some time, after a certain maximum time guys, you see that this inductor now just behaves like what guys? An ordinary wire. Great. So for instance, after a very long time now, the current that is going to be flowing through this inductor, like I said, is going to reach some maximum value or steady state. Okay, is going to reach this value as this graph is saying. That is the flat portion of the graph, the points where the equation of the graph is 0. Great. So this is that point guys. In this case guys, the current that is going to be flowing through this inductor, in fact the current that is going to build as a result of the presence of this inductor will no longer be changing. Great. So this is the value in which it is going to attain. Great. That therefore implies guys that we are just going to be looking at this inductor to be behaving like an ordinary wire that we all know, right? Just an ordinary wire. In such a case guys, we are therefore going to apply now our Kirchhoff's junction law at the junction M, because our goal is to find I1 and I2, right? Now we notice that what the loop 2 is also involved, and to do that we need to do that by Kirchhoff's law. Okay, we have to get the current I1 and I2 by Kirchhoff's law. Great. By default guys, if you apply the Kirchhoff's junction law at the junction M, we see that the Kirchhoff's junction law is simply saying that the sum of current entering the junction is equal to what guys? Those currents leaving the junction, right? We can see that I1 is entering this junction, right? I1 is entering junction M, while I2 and I3 are leaving. So we can tell them that our I1 has to be the same like what? I2 plus I3. Great. That therefore implies guys, since the equation said nothing about I3, we simply have to make I3 the subject. Therefore means I3 becomes I1 minus I2. Great. So guys, we can keep this our equation aside. Then now if we now apply Kirchhoff's voltage law for loop 1, Kirchhoff's voltage law of loop 1, keep in mind that for Kirchhoff's voltage law we are simply summing EMFs. When we start summing EMFs from a particular point around a closed loop and we arrive at that same point, guys, we simply equate to 0. So for instance, if we start from this point, we are moving in this direction. That is, we're moving for the direction of the flow of the current I1. We are therefore going to, in this case, guys, and keep in mind that when we are moving for the direction of current, we are going to have potential drops. Okay, when we are moving for the flow of current, we are going to have potential drops. As such, a negative sign accompanies the potential difference we are summing. But when we are arriving at a cell, the last terminal of the cell we touch gives us the value, or it gives us the sign of the EMF. Great. So at this point, if I start at this point, guys, I'm moving in this direction. I have touched negative and I've touched the positive last, right? So I'm going to have what? A potential gain here. Then at this point now, I am moving. I have arrived where, guys, I have arrived this resistor R1, right? So I am moving for the flow of current. That means that there's going to be a potential drop. I enter this direction. I am now going where? For the flow of I2, right? In the same direction as the flow of I2. That therefore means I'm going to have a potential drop, which goes to what, guys? A negative sign. So guys, what I'm simply saying is that we are therefore going to have 100 minus, keep in mind that potential difference from Ohm's law is given as what, guys? Current times resistance, right? That therefore implies the resistance of R1 is what? R1 is 10.0, right? So we have 10. Since the current that is flowing here is I1, we arrive at this point. The current flowing here is I2, and the resistance of R2 is what, guys? 20.0. So we have minus 20 equal to 0. So if we wrap things up, if we divide all through by 10 and we arrange, we are therefore going to have I1 plus 2I2, which is equal to 10. Great. So we can keep this our equation aside. Keep in mind, guys, that we have 3 unknowns here, 3 unknowns, but we're more interested in 2 unknowns. So we need about 3 equations to solve. Right. So now, if we now apply now the Kirchhoff's voltage law again, this time around on loop 2, this is now going to give us, in the same manner, guys, if we start from the junction M, we are coming this way for the flow of the current of I3, we are going to have a potential drop, right? So we are going to have negative here. Then now, guys, at this point, like I said, that this inductor now behaves as an ordinary wire after a very long time, since the current is going to approach some maximum value where di by dt in this case is 0. Okay, that's a change in the current with respect to time. Keep in mind that the current across the current in the branch that has the inductor now is now going to be changing. Okay, it's not going to be changing, so we can therefore say it is just given as di by dt. Okay, great. So now if you apply Kirchhoff's voltage law at this point now, guys, we now enter into this our loop, right? We can see that as we are coming up, we are going where? Against the flow of the current of I2. So when we are going for the flow of current, we are going to have a potential drop. When we are now going against the flow of current, we have a potential increase, which now takes a positive sign. So that therefore implies, guys, we are therefore going to have negative 30 I3, since the resistor R3 is what? 30, right? So we have negative 30 I3. Since in this case we are going against the flow of the current of I2, we are going to have what? Plus 20 I3. When we arrive at this point, we simply equate that to 0. Good. So guys, if we simplify a bit, we are therefore going to have our I2 to be the same like what, guys? 3 over 5 I1. Keep in mind that our I3 is what, guys? I1 minus I2, right? So if we substitute the value here and simplify, we're going to have our I2 to be the same like 3 over 5 I1. So guys, if we substitute our I2 equal to 3 over 5 I1 into this our equation, we are therefore going to have 11 I1 to be the same like 50. If we divide all through, we are going to have our I1 to be the same like 4.55 amperes. Wait, that's to 2 decimal places. We have it to be 4.55 amps. Wait. Alright. So guys, if we simply put this our value back into this our equation where we had I2 to be the same like 3 over 5 I1, we are going to see our I2 to simply be the same like 2.73 amperes. That's approximately. All right. So guys, that's how we can answer that problem. Then now they are saying that the switch is then reopened. Now just then, what are I1 and I2? All right. So now guys, when this switch is just opened, normally guys, what makes the current I1 to flow in this branch is what? This EMF, right? Great, great. So the variation of I1 is solely dependent on what, guys? On this EMF. The moment this EMF is taken off, I1 instantly becomes what? Zero. But you cannot say I3 and I2 becomes zero. No, because what, guys? Because I2 and I3 have what, guys? Have this inductor, right? Great. And the inductor is going to prevent the fast dying of the current. Great. So guys, initially, once we just open the switch, it therefore means that the circuit that has I1 is no longer complete, right? That therefore means that our I1 simply dies down to a zero. Good. 0 amperes. Great. Then now guys, for I2, we know that what I2 has the inductor, right? And the inductor is going to play its own part to make sure that the current does not instantly go to zero. As such, guys, our I2 is simply going to what, guys? Just before, in fact, just after, guys, just instantly, guys, just at that instant, wherefore this switch is open, guys, the current that is going to be flowing through this I2, that is the current I2, will not instantly be zero, but it will rather be what, guys? The same value it had here, which is what? 2.73. But since it will now flow in the opposite direction, namely, guys, this circuit, that is loop 1, is no longer complete. That therefore means that what? It now flows in this direction, that is opposite the direction of R3. Opposite direction of what, guys? I3. And since the question gave us here as a guide, though the question decided to give us as a guide that the currents in the direction that we have here are what? Positive, right? Then those in the negative direction are going to be negative. So since I2 now flows in the negative direction as opposed to I1, it is now going to be what, guys? Negative 2.73 amps. Great. That therefore implies we have I2 to be something like what? 2.73. But since it flows in the negative direction, guys, it has to be a negative value. Great. So that's it for it. That's said. Then now they are saying that that after a long time, that is with this switch still opened, after that long time, we should get the current I1 and I2. So guys, we know that initially when the switch was just open, right, that's I2 was still what? 2.73, right? Likewise, I3 had its value, which was different from 0. Now guys, the irony behind it is that with the inductor in place, the current that is going to be flowing at the current I1 and I3 are instantly not going to be 0, but after a very long time, guys, they are going to die down to 0. So after that long time, friends, we can simply tell them that when S is still open, that is with the switch still open, and guys, we know that there is no source that is going to drive a current to flow, right? No source. After that long time now, guys, I1 and I2 and I3 are going to die down to 0, guys. This is I3, not this is going to be I3, guys, not I1. Great. So I3 and I2, they are going to simply die down to 0. The function of our inductor here was just to prevent that, was just to take care of the fact that I1 and that's I3 and I2 should not instantly go to 0, but after some long time, they are going to eventually approach 0. Great. So guys, I hope you found the video useful, guys. If you found it useful, please give it a thumbs up. Subscribe to my channel if you want more great content, guys, because I bring forth good content in this channel, guys, every day of the week. Every day, guys, every day. You can't afford to miss, guys. You can't afford to miss. Great. So guys, as always, feel free to leave your worries in the comment section down below. Let me know what you think about the question, guys, and have a blessed day.